Welcome everyone to an exciting journey into one of the most familiar yet profoundly mysterious phenomena in the universe, the force of gravity. In our everyday lives, we tend to think of gravity simply as the force that exists between objects that have mass. It is something that is very easy to picture and even to feel in action. For example, all you need to do is step onto a set of bathroom scales. The number that appears on the display represents the force of gravity from the Earth acting upon your mass, which is what we commonly call your weight here on this planet. When we look up at the night sky filled with stars, we can imagine the gravity of the Sun keeping all the planets in our solar system locked into their steady orbits around it. And of course, everyone has heard about the incredibly powerful gravity near a black hole, which is so strong that not even light can escape its pull. Gravity seems straightforward and almost simple at first glance. However, everything changed dramatically with the arrival of modern physics. Today, we understand that gravity is just a small part of a much more complex phenomenon, thanks to Albert Einstein's general theory of relativity. But before we dive deep into that revolutionary idea, let us first review some basic foundational physics from the pioneering scientist who started it all. Everyone knows about Sir Isaac Newton, who was regarded almost like a god in the field of physics during his lifetime. There is a famous story about an apple falling from a tree that supposedly sparked a scientific revolution. In reality, Newton was simply observing an apple drop straight down from a branch while he was in a deeply thoughtful mood. He wondered why the apple fell directly to the ground instead of veering off to the side or moving in some other direction entirely. From this simple observation, he proposed that a force of gravity exists between any two objects, pulling them toward each other. His universal law of gravitation states that the strength of this force is directly proportional to the masses of the two objects and inversely proportional to the square of the distance between them. The formula that Newton developed is as follows: the force F is equal to the gravitational constant g multiplied by the product of the two masses m1 and m2, all divided by the square of the distance are between their centers. In mathematical terms, this is written as F equals g times m1 times m2, divided by r squared. Newton believed that objects move along the shortest path possible in order to conserve energy, and therefore that path would always be a straight line. In summary, Newton thought the apple fell because gravity accelerated it toward the ground. This mysterious pulling force was considered a core property of mass itself. To give some context, Newton's law works incredibly well for everyday situations, such as calculating the orbits of moons around planets or predicting the trajectories of cannonballs fired from ships during battles in his era. It formed the backbone of classical mechanics for centuries. However, Newton himself probably sensed that something was missing from his theory because he once admitted that he was not entirely satisfied with it. Interestingly, he initially conceived of gravity as a pushing force rather than a pulling one. Newton had no idea that he was partially correct about this deeper complexity, but his theory was accepted as absolute truth for the next 400 years, powering advancements in astronomy, engineering, and navigation across the globe. Everything changed when another genius, Albert Einstein, came along and presented his general theory of relativity. While working as a patent clerk in Switzerland, Einstein's challenge to Isaac Newton's ideas was initially laughed at or completely ignored because his concepts seemed far too revolutionary to be possible. He spent years refining his thoughts, publishing the full theory in 1915, and it fundamentally reshaped our understanding of the universe. The equivalence principle. The key to grasping general relativity lies in realizing that everything in a gravitational field falls at the same rate. It was actually Galileo Galilei who first concluded that all objects dropped at the same moment in a vacuum, where there is no air resistance, will fall at the same speed regardless of their mass. This idea was dramatically demonstrated during the Apollo 15 mission to the Moon. Astronaut David Scott simultaneously released a hammer and a feather, and both floated down to the lunar surface, landing at exactly the same time. This demonstration is known as the equivalence principle, and it shows that gravity accelerates all objects equally. So why do two objects fall together and hit the ground at the same moment? The surprising answer is that they are not really falling in the sense of being pulled by a force. Instead, they are at rest, and the space around them is curving. No actual force is acting on them directly. According to Einstein's theory, gravity is not a force between two massive objects at all. Rather, gravity is the curving of space and time in the presence of mass. When no forces are acting, objects naturally move in straight lines through this curved spacetime. Einstein proposed that smaller objects are not pulled by larger ones but are instead pushed downward by the space above them. He insisted that there is no such thing as a gravitational force in the Newtonian sense. To expand on this, imagine a flat trampoline representing flat spacetime. If you place a heavy bowling ball in the center, it creates a dip. Now roll a marble nearby. It will curve toward the bowling ball not because of a mysterious pull but because the surface itself is warped. In Einstein's view, matter does not just curve the structure of space, it also curves time. This unified four-dimensional fabric is called spacetime, which combines the three dimensions of space, length, width, and height, with the fourth dimension of time. The more massive an object is, the greater it warps the spacetime around it. For instance, the Sun warps spacetime enough to keep Mercury orbiting close and Pluto far out, all following curved paths that appear as elliptical orbits from our perspective. Einstein explained that the apple falls from the tree and planets orbit stars because objects follow curved paths, known as geodesics, in this warped spacetime, and these curves are what we perceive as gravity. A helpful analogy is to picture the Earth placed on a flat grid representing spacetime. The mass of the Earth bends the grid downward, creating a gravitational well. Any object nearby rolls down into this well, much like a ball rolling into a depression on a rubber sheet. The Moon also warps spacetime with its mass, but the gravitational field between Earth and the Moon is not strong enough to pull the Moon crashing down toward us. Instead, the Moon continually slides along the edge of Earth's gravitational well with a sideways velocity, resulting in a stable orbit that has lasted billions of years. This balance is delicate. The Moon is slowly spiraling away from Earth at about 3.8 centimeters per year due to tidal interactions. We can also understand how gravitational wells around planets work by looking at how spacecraft are launched and navigated. To change a spacecraft's direction from its initial path or to increase its speed, engineers use the curved spacetime or gravity around other planets in the solar system to create an effect called a gravity assist or slingshot maneuver. This technique propels the spacecraft in a new direction at a higher velocity. The closer the spacecraft gets to the planet and its gravitational well, the faster it will travel afterward. Famous missions like Voyager 1 and Voyager 2 used gravity assists from Jupiter and Saturn to reach the outer solar system and beyond, saving enormous amounts of fuel that would otherwise be needed. In summary, objects in the universe attract each other because spacetime is curved by mass. The closer something is to a large mass, the faster it accelerates toward it. This curvature explains not only falling objects but also the precise predictions of planetary motions that Newton's law approximated so well for weaker fields. What about the gravitational field we mentioned earlier? A gravitational field is essentially a region of influence in space around any object with mass where other objects experience a force. The Moon has a weaker gravitational field than Earth because of its smaller mass, which is about 1/6 of Earth's, leading to lower surface gravity. Even the International Space Station, orbiting about 400 kilometers above Earth's surface, feels the pull of Earth's gravity. Surprisingly, the effective gravity in orbit around a planet is nearly the same as on the surface. In fact, it is about 90% of surface gravity. If you weigh 100 kilograms on Earth, you would weigh approximately 90 kilograms while aboard the International Space Station, though astronauts do not feel this because of their motion. Microgravity, the state of free fall. But if gravity is so strong there, why do astronauts appear to float in a weightless state? The reason astronauts look like they are drifting in space is that everything, including the International Space Station and the astronauts themselves, is in free fall together in the vacuum of space. This condition where people and objects seem to have no weight is called microgravity. The space station, satellites, and everything on them are constantly falling toward Earth. While the International Space Station is falling, it is also moving sideways extramellix at an incredible speed of about 28,000 kilometers per hour, pulled by Earth's gravity into a circular orbit. This orbital velocity matches the rate of fall, creating a perpetual free-fall state that has allowed continuous human presence in space since the year 2000. There are several ways to prove Einstein was correct. The acceleration due to gravity at Earth's surface is 9.81 meters per second squared. Zero gravity at the planet's center. The reason gravity pulls you and other objects toward the ground has nothing to do with the planet's core in the way you might think. All mass bends and curves space-time, and that curvature is the essence of gravity. If you could journey to the center of the planet, there would be no net gravity. You would be equidistant from all the mass surrounding you, effectively at the balance point of the space-time curvature, floating weightlessly around the core. This principle applies to any spherical mass distribution, as proven by Newton's shell theorem. Gravitational lensing. One of the most important pieces of evidence is gravitational lensing. This occurs when a massive celestial body, such as a galaxy or galaxy cluster, bends light from more distant objects. Sufficient curvature of spacetime can deflect light paths visibly around the massive object. This effect has allowed astronomers to detect invisible galaxies, dark matter distributions, and even exoplanets. A famous example is the Einstein cross, where a quasar appears as four images due to lensing by a foreground galaxy perfectly aligned. The Hubble Space Telescope and now the James Webb Space Telescope have captured thousands of such lensed images, mapping the universe's large-scale structure. Gravitational redshift. In the year 2018, scientists observed a blue star named S02 as it made its closest approach to the supermassive black hole Sagittarius A star at the center of our Milky Way galaxy. If Einstein's theory holds, the black hole would curve spacetime and stretch the wavelengths of light from the star, causing a gravitational redshift. The intense gravity saps energy from the light photons, shifting them from blue to red. Exactly as predicted, the star glowed redder at its nearest point, providing direct evidence in our galactic backyard. This observation required decades of precise tracking with telescopes like those at the Keck Observatory in Hawaii. It seems Einstein was completely right about gravity. But here is the big problem. In its current form, general relativity is incompatible with quantum mechanics, the theory that describes the world at microscopic scales. Quantum gravity is a branch of theoretical physics attempting to describe gravity using quantum mechanics. So far, no theory has been widely accepted or experimentally confirmed. Researchers know that at certain points inside black holes, at the singularity where density becomes infinite, Einstein's theory breaks down. Current candidates include string theory, which posits tiny vibrating strings as fundamental building blocks, and loop quantum gravity, which quantizes spacetime itself into discrete loops. Scientists are searching for extreme spacetime curvatures where general relativity fails. They believe that within the next 10 years or so, observations from gravitational wave detectors like LIGO, the Event Horizon Telescope imaging black holes, or particle accelerators might push general relativity to its limits. Another genius will likely emerge to point out where Einstein was incomplete, perhaps unifying all forces into a theory of everything. Let us hope we do not have to wait another 300 years for that breakthrough, as humanity did between Newton and Einstein. The quest continues, driving telescopes, colliders, and minds toward the next horizon of discovery.